In this example, we're asked to look at the case here of having a rigid bar which is pinned to ground there at D. It's supported by two rods here, 1 and 2, one at end A and the other one at point C. And then there's this applied force P acting downward there at point B. We're asked to find the axial stresses in the rods after this load P is applied. What's the resulting rotation theta for the beam of AD, assuming that theta is small? Our first step, of course, is to draw FBDs. So let's draw free body diagrams of segments 1 and 2. We know that they carry only an axial load, so this will be F1 on both ends here. By Newton's third law, there's an F1 force acting on the bar. The load carried by member 2, it's a 2-force member, so that's F2. Newton's third law, equal and opposite force there of F2. We have an applied force P acting here, and of course, over here at D, we have reaction forces of dx and dy. The coordinate axes I'm going to use is x is going to be to the right, y is going to be up. So positive k is going to be coming out of the screen, and therefore by the right hand rule, that would be a moment which is positive is counterclockwise. Okay, so what I'm going to do is equilibrium first. That's usually our first step. So we have equilibrium analysis, and what I'm going to do is simply do a moment equation about D. That's a good choice because we got these reactions of dx and dy, which I failed to put down here, acting at D. So doing a moment about D gets rid of that. F1, it has a moment arm of 2a plus b. It's in the negative k. F2 has a moment of b, is also in the negative k. And the applied force P, it has a moment arm of a plus b, and that's in the positive k. Putting those together for equilibrium is a 0. So right now we recognize the problem. We have a statically indeterminate bar here because we're supporting it at 3 places. We're supporting it at rod 1, rod 2, and at D, and that gives us too many unknowns to solve for our reactions. So in anticipation of needing to have the elongation information, let's write down those elongation equations. So for segment 1, or rod 1, we would have the E1 here is equal to F1 L1 divided by E1 A1. So this becomes simply F1 L over EA. Rod 1 has a length of what we're calling L. And for rod 2, the elongation equation, the standard form, would be F2 L2 divided by E2 A2. So the length of segment 2 is 2L, so this becomes 2 F2L divided by EA. So that is my third equation, which is coming from the elongation. This simply tells us the relationship that exists between the elongation and the axial load. What we now need to do is to be able to relate the two axial deformations. So that requires our compatibility equation. So as we think about this rod is a rigid, or the bar is a rigid bar, so as these rods deform, the bar is just simply going to be rotating about point D. So to go back up to my figure right next to my FBD, what I have here is the elongation here at end A is what we call E1. The elongation there at that point, which is C, is the elongation there of E2. And the rotation angle here is a theta. So from our figure for small theta, theta here, which is the inverse tan of E2 over B. E2, again, is the deformation there at B. The distance from D to B is lowercase b. So for a small angle, the tangent and the angle are one and the same. So this is approximately equal to E2 over B. I can also write down the same kind of equation to relate E1 back to the distance to point D. So that distance to point D is 2a plus b. For small angles, this becomes, of course, E1 divided by 2a plus b. So this is our compatibility, is that the bar doesn't deform, it only rotates about D. So if I take these two equations, if I equate them, I get E2 divided by B is equal to E1 divided by 2a plus b. So our compatibility equation comes out to be that the elongation of rod 2 is equal to the ratio of b divided by 2a plus b times the elongation there of 1. So that is our fourth equation that we need. So what I'm going to do is solve these, and the steps I'm going to take are, I'll first combine together equations 2, 3, and 4. 2, 3, and 4 say that 2F2L divided by EA is equal to B divided by 2A plus B times E1, well, that was F1L divided by EA. So from this, I get that the ratio between the load carried by 2 and the load carried by 1 is 1/2 the ratio of the distance B divided by the distance of 2A plus B times F1. So again, this gives us the proportionality, if you will, between the loads of rods 1 and 2. So this is going to be our equation 5. I haven't not yet used the first equation, which was equilibrium. So I combine 1 along with my relationship here between F1 and F2. So I get F1 times 2A plus B plus 1/2 B divided by 2A plus B times the moment arm of B for F2, that's F1 here, and on the right-hand side it's A plus B divided by P. What have we done? Well, we've got things down now to a single equation and a single unknown. So from this, F1, therefore, is equal to the ratio of A plus B divided by 2A plus B plus 1/2 of B squared divided by 2A plus B. So we can put our numbers in there, and this becomes all times P. So again, putting the numbers in gives us that. We found the ratio there between F1 and F2. That was 1/2 B divided by 2A plus B times F1. So F1, that number will go in there, and we get F2. So all this was just to find the load that's carried by members 1 and 2. We finally get to answering part A, and part A says that the stress in 1 is the axial load divided by the cross-sectional area of A, so we've got enough there to calculate that. Sigma 2 is the load in member 2 divided by A, so we can calculate that. And keep in mind that both of these are plus, and that's no surprise, in that both of those rods, 1 and 2, are in tension. Then it asks us to find the small angle of rotation. I'm going to pick the one equation between theta and E2. So I take the equation for E2 divided by B, E2, keep in mind, was F2 times 2L divided by EA. So we need to subtract or divide there by B. So this gives us a number for that. The point of the problem is that this problem is statically indeterminate. It's got 3 supports, and that's too many supports that we can solve from treating everything as being a rigid. But fortunately, we know something about the compliancy of rods 1 and 2 in terms of our elongation equations. So just to go back on what we had just talked about, we first write down E in equilibrium. That is back here at equation 1. We write down our elongation equations for rods 1 and 2. And finally, we lace it all together here with a compatibility equation. What's the relationship between elongations 1 and 2? And that was compatibility came from looking at the rigid rotation of the bar. At that point, we had 4 equations and 4 unknowns, and we solve for the loads, and from the loads we get the stresses, and then from the elongation we can get the rotation.